To video lecture number 2. Today we're going to delve a little bit farther into subatomic particles and differentiate between atomic mass and atomic number. Ready? Two subatomic particles have mass, protons and neutrons, both in the nucleus, remember from our previous notes. The number of protons an atom has is also called its atomic number. We're going to find that on the lower part, and that's of the element symbol, and that's going to differentiate each atom from one another. Remember, the number of protons differentiates helium from hydrogen, from oxygen, from nitrogen. Well, they're also going to have corresponding atomic numbers that are different. That's what we're going to use. Okay? The atomic mass, is it the same as the atomic number? No. We've got to calculate the atomic mass, or from the atomic mass, calculate the neutrons, either or. But here we go. Calculate the atomic mass, we add the number of neutrons and the number of protons. I said it backwards, I apologize. Number of protons and number of neutrons, because both have mass. Okay? Those are the species, the subatomic particles in the atom that have mass. We'll add those up. That's going to give us our atomic mass. If we start with the atomic mass, we look at our periodic table, we find the atomic mass of nitrogen, we see that it has 7 protons. In order to calculate how many neutrons it has, we've got to go backwards. So if we start with the atomic mass, to find the number of neutrons, we're going to end up subtracting the atomic number, or the number of protons, from the atomic mass, which is the total mass, the protons and the neutrons. Okay? So here's in our periodic table, this is what the element carbon is going to look like. Let's just go through and make sure we know what each of these numbers and symbols means. First off, the symbol C for carbon, definitely capitalized. If there's 2 letters in the symbol, you're going to find the second letter is lowercase. Okay? 6 on the bottom, most important, protons. The number of protons, and that is, of course, the atomic number. Okay? Up top is what we call the atomic mass, or the mass number. Either way, you might see atomic mass, you might see mass number. Okay? Mass is the key part. What has mass? Protons and neutrons. We add them up. So let's do a sample calculation. Okay? To calculate the number of neutrons that this carbon atom has, we need to subtract first. Start with the atomic mass, which in this case is 6. I'm sorry, I misspoke. The atomic mass, which in this case is 12. From that, we're going to subtract the number of protons, the atomic number, which is 6. 12 minus 6, atomic mass minus atomic number. It's going to give me neutrons, which in this case is 6. Okay, pretty easy math. Not too hard. Ready to go? There for now. There are actually 2 forms of carbon found on the planet. Carbon 12, carbon 13. These are called isotopes because they have the same number of protons, but they have a different number of neutrons. Okay? I'm going to add protons and neutrons together to get me my mass. Here, 6 and 6 is 12. In this case, 6 and 7 is going to be 13. Okay, what stays the same from our previous notes, the protons. If it's carbon of any form, it has to have 6 protons. So that's a given. Let's get that straight right now. Okay, now we can play math games based on atomic mass and the different isotopes. So let's get right into it, and we'll read a problem, and I'll work you right through all the calculations. Oxygen 3 isotopes, 16, 17, and 18. Oxygen 16 has an atomic mass of 15,995, and its natural percentage abundance is 99.759%. That means out of all the oxygen atoms out there, most of them are oxygen 16, which has a mass of 15.995. Okay? Oxygen 17, it's got a mass of almost 17, but look at its percentage, 0.037%. Really small. The oxygen 18, 0.2%, weighs almost 18. Well, I'm going to use all these numbers to figure out what the average atomic mass of oxygen is. Okay, ready? This is what we do. Step 1, I need to convert the percents into decimals. Generic definition of percent is
Part over whole times 100.
no matter what you're taking the percentage of, free throws, batting average, percent boys in the class, percent students wearing hats. The part is the number that we count. The whole is how many tries we took or how many students there are. Divide them, multiply by 100. Well, I'm dealing with a percent here, so I have to back calculate into this, so I need to divide both sides by 100. First step. So I'm going to divide 99.759 by 100. I'm going to get 0.99759. Keep all the digits now, please. Remember, we're going to round at the end, not in the beginning, at the end. Never in the middle either, only at the end. When do we round? The end. Okay, got it. Trick. If you don't have a calculator, you just got to remember which way to go. You move the decimal place over 2 spots, same as dividing by 100. So, 0.037 is going to go to here, 0.204 is going to go here. Good. I'm going to multiply the decimals by their relative masses. Relative meaning this particular percentage went with a specific mass, if you remember back in the problem. You look up easier, it's easier for you to see it on your paper. Here it's on my previous slide. So I'm going to put the numbers in. 0.995 is going to come here. It was relative to the mass of oxygen 16. It was the most abundant. And I'm going to multiply those two numbers together, and here I got a number almost the same. Notice it's the bulk of it, okay, percentage-wise. All right, I'm going to fill in the rest. 0.0037 comes down, its mass, multiply it, okay? Bring down the 0.0024, multiply it by its relative mass. Here we go. Now, last step. Take these three numbers, I'm going to put them down here into my math problem, and I'm going to add them up. When I come up with it, bam, my average atomic mass, 15.994. I'm going to step aside. If you still need to catch up on any of these numbers, do that. Press pause on the video and do that. Ready? Here, go. Okay, I'm back. You unpaused it? Good. Moving on. Let's compare the numbers. Look in your periodic table. What do you see the number of oxygen is in the upper right-hand corner? 15.9994. They're what? They're the same. They're the same. That means that the atomic mass numbers on the periodic tables are really the average atomic mass, okay? The average atomic mass. The reason why this is important is I have a bag of oxygen atoms. Some are going to be oxygen 16, some are going to be oxygen 17, some are going to be oxygen 18. As a matter of fact, based on those percentages, which these very famous scientists with very fancy instruments determined, oxygen 16 is the most abundant, 99 point something percent, right? So if I reach in, I got 99 of those in my bag, I got one of the other and part of another. What am I going to pull out? Probably the oxygen 16. But when I'm dealing with a tank of gas, I can't tell you how many atoms there are of oxygen 17 and oxygen 18 are in there. So what I do is I use this average to make sure that math is better, more accurate, and more precise, okay? So if I did pick one out at random, would I actually get one that was 15.994? Do you think? No, I wouldn't. So as I go away, lecture's over, your homework for tonight before class, why? Why is it when I reach into that bag, I can't actually get one that's 15.994? Video lecture number 2 is over. See you guys tomorrow in school.